Assalamualaikum and hi everyone. In this video, my group will be talking about sustainable energy solutions in applying thermodynamics to improve solar. We are from group B2. Let's get started. And this is our team members. We have Aliana Sasha binti Rashidi, Nur Farshia Zahra binti Nur Hizam, Nurul Bashira binti Muhammad Fazli, and Nur Nabila Balkis Hanani binti Muhammad Shaiful Akmal.
Moving on into the introduction, solar energy is a renewable energy source derived from the sun's radiation. It is captured and converted into usable energy through photovoltaic system and also solar thermal system. So the photovoltaic system, it converts sunlight directly into electricity using semiconductor. Meanwhile, for solar thermal system, it uses sunlight to heat fluids, which can be used for heating or to generate electricity via turbines. And not only that, solar energy is clean and sustainable, making it a key focus in the global shift towards green energy. Next is the common challenges. Okay, we have two. The first one is high initial cost. Okay, although the costs have decreased, installation, infrastructure, and maintenance, it still remain expensive, especially for large-scale system. And for the second one is environmental and material concern. So like the production and disposal of the solar panel involve like materials such as silicon, cadmium, and also lead, which can be environmentally harmful if it not handled properly.
Hi, my name is Farisha and I will be talking about the principle of thermodynamics. So, the principles of thermodynamics describe how energy and heat behave in physical systems. For the first one is the zeroth law. The zeroth law establishes the concept of temperature by stating that if two systems are each in thermal equilibrium with the third system, then they are in thermal equilibrium with each other. Next is the first law. The first law, or the law of conservation of energy, states that energy cannot be created or destroyed, only transferred or transformed, such as from heat to work. On to the next one is the second law of thermodynamics. The second law introduces to the concept of entropy, stating that entropy of an isolated system always increases over time. Natural processes tend to move toward a state of greater disorder. And for the last one is the third law. The third law states that as the temperature of a system approaches absolute zero, 0 Kelvin, the entropy of a perfect crystal approaches zero. Here are a few examples of the zeroth law of thermodynamics, the first law, the second law, and the third law.
Let's look at how solar energy is being applied in industrial setting. A great example is Nestle Malaysia, which installed a rooftop solar PV system at its Shah Alam and Chembong factories. These facilities produce items like Milo, Nescafe, and instant noodles. This solar system generates around 2.4 gigawatt hour per year, directly powering operations such as machinery, lighting, HVAC, and production lines. From a thermodynamic perspective, the solar energy aligns with daytime factory loads, minimizing energy loss. It reduces reliance on the grid, improving first law efficiency by cutting out unnecessary energy conversions. It also boosts second law efficiency as energy is used close to where it's generated, increasing overall system exergy. The impact is clear. Nestle cuts about 1,200 tons of CO2 yearly and supports global goals like net zero by 2050. For contrast, the Kipak Bukit Selamba project, part of Malaysia's LSS2 program, use single-axis tracker to follow the suns to improving energy output and thermodynamic performance. It generates enough electricity to power 8,000 to 10,000 homes annually. This example show how industrial solar adoption isn't just possible, it's smart, sustainable, and thermodynamically optimized.
What are the challenges and solutions in applying thermodynamics to improve solar? For the first one, we have heat loss in solar thermal system. This problem can be solved by improving insulation and vacuum tubes to reduce conduction or convection. The second one is we can use selective surface coatings to reduce radiation loss. The second problem is energy storage difficulty. And the solutions are use molten salt thermal storage that are used in CSP systems to store high temperature energy. The second one is use phase change materials, PCM, to store latent heat with high density. And the last challenge is mismatch between solar input and system needs. How can we solve this? Well, we can use spectral splitting to direct UV or visible light to PV and IR to thermal. And the second solution is combine PV plus thermal hybrid system, PV over T, to capture both electricity and heat.
My name is Nurul Bashira. So I'm present about case study and data analysis about improved solar panels efficiency in Malaysia's hot and humid climate. Background of this case study is Malaysia's tropical weather means high solar irradiance but also high ambient temperature, so average daytime temperature is from 30 until 35 degrees Celsius. Unfortunately, solar panel efficiency decreased from 0.4 until 0.5% for every 1 degree Celsius rise above 25 degrees Celsius. So, in this project, tested passive cooling solution to reduce overheating of solar panels. Okay, problem statement of this case study is 1. Solar panel efficiency drops by 0.4 and 0.5% for every 1 degree Celsius above the optimal 25 degrees Celsius. Second is excessive heat reduces energy output and overall system performance. Third is high temperature causes faster wear and degradation of panel materials. And last, problem statement is lack of effective thermal control results in underutilized solar. For this slide, I will present about thermodynamic principle applied in this case study, which is second law of thermodynamics. Second law of thermodynamics is energy system naturally move toward higher entropy disorder. It is because to reduce entropy generation, thermal losses. The study used aluminium heat sinks to improve heat dissipation via conduction and natural convection. And this helps maintain to lower and more stable panel temperature, reducing efficiency loss. So what happens when this applied in this case study? So the improvement is first install passive aluminum heat sinks on the back of the solar panels. Second is utilize natural convection and conduction to dissipate heat. Third is apply second law of thermodynamics, reducing entropy, heat loss, and increase efficiency. Fourth is no electricity required. That's a fully passive system. And last is tested on real setup at University Malaya, Kuala Lumpur. Setup on the rooftop. Okay, this is a data analysis about this case study. It's a comparison without cooling and with cooling. First is average panel temperature. Without cooling is 58 degrees Celsius, and with cooling is 42 degrees Celsius. So it's lower than without cooling. Second is panel efficiency in the percentage. So without cooling is 14.8%, but with cooling it's more than that. It's 17.3%. That is daily energy output. So daily energy output, which is daily energy, is without cooling is 5.1 kilowatt, and with cooling is 6.2. It's more than without cooling. Fourth is energy improvement. Without cooling is don't have any energy improvement, but with cooling energy improvement is positive 21.6%. So have improvement in cooling system. So cooling cost and with cooling system is no cost, but without cooling it's 18 ringgit per panel. Okay, last is ROI payback period. So for the without cooling it takes 6.3 years, but with cooling it takes 5.2 years.
So into this part about the solution and technological advancement, the first one is applying thermodynamic optimization, which is we use the thermodynamic analysis like exergy analysis to identify and minimize energy losses in PV and also solar thermal system. Not only that, it also can design system based on maximum energy output per unit of entropy generated, increasing overall efficiency. And the second one is recycling and sustainable materials, like develop solar panels using non-toxic and recyclable material, and also set up system for end-of-life recycling to reduce the environmental impact and recover valuable materials.
In conclusion, solar energy offers a highly sustainable path for industrial use in Malaysia. Thanks to the country's abundant solar potential and supportive government initiative. By applying the first and second law of thermodynamic, industry can maximize energy efficiency, reducing conversion loss, and improving exergy by using solar energy close to where it's needed. We saw this in Nestle Malaysia, where a rooftop PVS power operations like sterilization and packaging during a peak sunlight hours. Similarly, with a key parks solar plant use a solar tracking system to enhance output and thermodynamic performance. While challenges like intermittency and hype upfront costs remain, they can be managed through the technological upgrades, real-time energy management, and financial incentive. There's also have a few recommendations that we can use in the future, which is the first one, adopt smart load scheduling energy intensive tasks with a peak solar output. And the second one is integrate thermal storage or battery system, which is to address intermittency and balance loads. And the third one is utilize solar tracking technologies, which is to increase efficiency and energy yield in a large scale application. Ultimately, combining thermodynamic optimizations with a smart industrial planning and policy support is critical to accelerating the shift toward a cleaner, more efficient industrial energy system in Malaysia.
As we can see, the last page of this slide is visual aids of thermodynamics that apply for improving solar